Let's start with something your brain already knows very well. That is, if you attach a mass to a spring and pull it to one end, what would happen? So, you would expect the mass to be pulled to the left towards the center, and as it moves to the left, its velocity would increase. And then after it crosses the equilibrium position, the spring would start compressing and the velocity will start reducing and become zero at the extreme left. And if there is no loss of energy, a similar pattern would be visible, that is speeding up and slowing down on the way back. And this is also familiar from real life. So what we're going to do now is take this motion that we already understand intuitively and write two equations for it so that we can understand it even more deeply. But before we write the equations, let's walk through what happens to the velocity and acceleration as the mass completes one full oscillation. And we will start from the extreme right, which means in our equation x is equal to a cos omega t plus phi, the phase angle is 0. Now, at this instant, the mass is at rest or velocity is 0. However, it is quite clear that the spring is fully stretched. That means the spring is pulling on the mass to its max and therefore offering maximum force, which means acceleration is also in this direction and at its maximum. Then this implies that the velocity should increase rapidly from its current velocity of 0 meters per second. Also notice the sign of acceleration and velocity is negative since both are pointing in the negative x direction. And to be more precise, the velocity here is 0. It actually has no sign, negative or positive. But the moment the motion starts, it would be negative. So the mass is now moving from its totally stretched position towards a equilibrium position, and the velocity starts increasing. However, you see the force on the mass is reducing since the spring is becoming less and less stretched. Well, reduced force also means reduced acceleration. So you can see that the velocity is increasing, but the acceleration is reducing. And then at the equilibrium position, the spring is at its natural length, that is 0 stretch, and therefore force and acceleration drop to 0, while the speed of the mass is at its maximum. Now, a lot of students ask, if the force is 0 at this point, why is the mass still moving? The reason is Newton's first law. At that instant, there is no net force acting on the mass. So there is nothing to stop the mass or suddenly change its velocity. It simply continues in its state of motion, carrying the kinetic energy it gained from the spring as it moved in. Next, we see that the mass moves past the equilibrium position and starts compressing the spring. And this compression in the spring means that now this spring is pushing back on the mass in this direction, which therefore means the direction of acceleration has reversed and become positive. However, the direction of the velocity is still negative, and therefore the velocity should start reducing. And as the spring compresses more and more, the force and acceleration in this direction keeps growing and reaches its maximum when the mass reaches the extreme left. And at this instant, the spring is completely compressed, and this means maximum force and therefore maximum acceleration is acting on the mass in this direction. However, at this point, the mass has come to rest. That is, its velocity has become 0. And now the mass starts its return journey, and its velocity once again starts increasing because of the acceleration provided by the spring force. And its velocity reaches its maximum at the equilibrium position, where you can see the spring is in its natural state, that is, no compression or stretch. Therefore, no force or acceleration offered by the spring. And after it crosses equilibrium, the spring starts to stretch once more and the direction of the force and acceleration flips again, causing the mass to slow down until it comes to rest back at the extreme right. So in one full cycle, we've seen that the mass is fastest in the middle and slowest actually stopped at the ends. And now we will capture this pattern in equations. So we will first find an expression for velocity of the mass as a function of time. Now, since we already know the position of a particle is given by the equation x is equal to a cos omega t plus phi, from calculus, velocity is just the first derivative of the position. So what we get is velocity at any time t equals minus omega a sine omega t plus phi. That can also be written as minus a 2 pi upon t sine 2 pi t upon capital T plus phi. And this equation tells us that velocity is sinusoidal in time. And since this part of the equation is a constant for a given motion, what brings about a change in velocity is this part that can vary between -1 and +1. That means the maximum speed occurs when sine omega t plus phi is equal to plus or -1. So Vm is equal to omega a, and just as a is the amplitude of displacement, Vm is the amplitude of the velocity graph. The largest speed the mass reaches during its motion, and we use Vm as a label to describe it. So as a concrete example, let's take xt is equal to 10 cos 2 pi t upon 6, where 10 meter is amplitude, 6 seconds is the time period t, and the phase angle constant phi is 0. That means it is starting from extreme right at t equal to 0. Then using a general formula, the velocity for this motion is Vt is equal to minus 10 2 pi upon 6 sine 2 pi t upon 6. So let us do a check on this equation and find the velocity at time t equal to 0, and we calculate this equals 0 meters per second. And that's what we see here as well. At t equal to 1.5 seconds, when the mass is at its equilibrium position, we expect the velocity to be pointing leftward and at its max. Well, we find the calculated velocity as minus 10.47 meters per second, and that is what we see here in the simulation as well. Next, we calculate the velocity at t equal to 2 seconds, and what we get is minus 9.07 meters per second, which means the mass is still moving to the left fairly fast, but the velocity has reduced due to the compression in the spring that is now offering force in the opposite direction. And that matches with what we see in the simulation as well. Next, let's calculate velocity at t equal to 5 seconds, and that would be plus 9.07 meters per second. So you see, this one equation correctly captures both the magnitude and the direction of velocity at any instant. Next, to get an expression for acceleration of this mass, we differentiate the velocity with respect to time, and when we do that, what we get is minus omega square a cos omega t plus phi. That can also be written as minus a 2 pi upon t square cos 2 pi t upon capital T plus phi. And of course we know what comes next. That is, the value of acceleration also oscillates between plus omega square a and minus omega square a, because this cosine function varies with time between plus and minus 1. So the maximum magnitude of acceleration is am is equal to omega square a. Once again, we can draw a graph for acceleration against time. So for a phase constant phi equal to 0, we get a graph like this. Now you can see that the magnitude of acceleration is 0 if the cosine is 0. And this happens when the position of the particle is at x equal to 0, where the spring is in its natural state. No stretch, no compression. On the other hand, the magnitude of acceleration is at its max when the cosine magnitude is maximum. And this happens when the particle is at an extremity where it has been slowed down to a stop and its motion is about to reverse. Again, you may like to calculate the acceleration at various times for this particular SHM and see if this equation works. So the equation for acceleration for this one can be written as AT is equal to minus 10 2 pi upon 6 square into cos 2 pi t upon 6. So let us see what is the value of acceleration at t equal to 0 seconds. And what you find is this equals minus 10.97 meters per second square. And this is the maximum acceleration or the amplitude of acceleration, which also makes sense because you can see the spring is totally stretched out and therefore experiencing maximum force in this direction and therefore maximum acceleration. At t equal to 1 second, acceleration is minus 5.48 meters per second square. That is, it continues to act in this direction but has reduced in magnitude, which aligns with what we see here. That is, the spring is less stretched now, which means less force and less acceleration. At t equal to 1.5 seconds, acceleration becomes 0, which should not be surprising considering the spring here is in its natural state or unstretched and hence exerts no force on the mass and therefore no acceleration. Let us now calculate the acceleration at t equal to 3 seconds and we find this equals plus 10.97 meters per second square. That seems very correct considering that now the mass is at extreme left where maximum force is acting in this direction. At t equal to 5 seconds, we find acceleration is equal to minus 5.48 meters per second square, and this also seems in place considering now the spring is in a stretched position and is being pulled in this direction. That is, the force is in this direction and therefore the acceleration should also act in this direction. Okay, now if we compare the expression for xt and at, we see something neat. That is, at is equal to minus omega square xt. And this equation reveals something very useful. That is, the acceleration of the particle is always opposite its displacement, because you can see the minus sign here. Also, you can see the two quantities are connected by a constant, and this gives us a quick test for SHM. That is, whenever in an oscillating system you find that A is equal to minus kx with k a positive constant, you can say this is simple harmonic motion and identify omega by writing omega square is equal to k. So if this lesson felt tough, that's normal. SHM is one of those ideas that looks scary at first, but if you sit with the graphs and equations for a bit, calculate a few values and connect them to the motion you see, it will stop feeling mysterious and start feeling like a very predictable, very manageable pattern.